So when you create a ETABS model, first step number 1 is not dead load, not live load, not anything, just run a modal analysis and study the modes, isolate the problems. We spend in our office when we have a new project, believe me, my personal input in the project is 90% related to the balancing of the dynamic response, mode shapes and natural periods. That's what we work with, and once we get that right, the rest will be okay, right. So the modal analysis determines the inherent natural frequencies. Each natural frequencies is related to a natural period and a mode shape. The period is the time it takes to complete one cycle of deformation. The mode shape is the normalized deformation pattern during that deformation. The number of modes is typically equal to the number of degrees of freedom of a structure. That's interesting. In a typical tall building, how many degrees of freedom are there? A few million. As many nodes as you have created in the structure, that many, not nodes, nodes multiplied by 6. Each node has 6 degrees of freedom. So in reality, the total natural periods or natural frequencies of the structure are equal to the total degrees of freedom in a structure, which could be in millions for a large structure. Imagine that a structure can deform theoretically in a million ways. Now the question is, which of those million ways are interesting to us? And that is something that we call modal extraction. That means extract the useful modes from that information. Which modes are important? Which modes are useful? Which modes are superfluous? Which modes are redundant? Which modes are not something that I want to see? Which modes I want to block, right? This is all about studying the frequencies and the corresponding mode shapes, right? Mr. Ashraf, first time when we invited him to AIT to talk about this one, I think is 2005 or something, or before that, in Milton Bender Jr. Milton Bender, so he talked about at that time, I'm talking about really almost 18 years, 17 years ago, and he gave this example, and that normally for tall buildings we talk about the number of modes and which modes to be considered, right? And we say first mode, second mode, third mode. However, if you put a small antenna on the building and model it, a small antenna, you will see that first several modes will be actually the modes of that antenna, not of the building. So then if you start studying theoretically first 3 modes, you will get nothing, because those modes do not relate to the building. We need to be able to identify which mode is a building mode or a global mode, which mode is a local mode, which is a lower mode, which is a higher mode, which is a superficial mode, which is a predominant mode. There are 10 different ways to call these modes. So unless we understand them, we will not understand the building. So I think we don't need to read this. I'm talking about all of this. So basically, natural period, like I said, I started from the doctor's example that the entire human health is related to the pulse. So natural period is the pulse of the structure. So if you can first of all determine the pulse, then read and understand the pulse, then you are a structural doctor. Really, think of yourself as a structural doctor that is trying to read the pulse of the structure or understand the pulse of the structure and can prescribe medicine based on that, can fix things based on that, right? So have a stethoscope with you, go to a structure and then try to measure. Actually that is true, but that's what we are doing, right? To measure the pulse. We actually can, as you know, measure the pulse of the real structure, right? And we can also estimate. So this is estimation, model. So You can get a lot of information. First of all, okay, let me start. First of all, you can check whether your model is correct or not, because a certain dynamic response is expected from a building or a structure. If your model is not giving that response, probably your model is wrong. So that's a first check on the most important use of the dynamic analysis is to check the model. If the model is correct and still the dynamic response is not what you expect, then the structure is wrong. Then you need to fix the structure, right? So if you get a wrong dynamic or unexpected dynamic response, first of all you should know the difference between an expected and an unexpected dynamic response to check it. That's number one. And then if you find an unexpected dynamic response, then you should check your model and see where the problem might be, right? And if the model is all correct and you are confident, then you better check your structure, because then something is wrong with the structure. Because dynamic response expectation is known, like pulse is known. Your pulse, human pulse, should be between 60 to 80 for a healthy person, or 60 to 100 or whatever the number, right? So if your pulse is outside that, something is wrong, you better see a doctor immediately. But the point is, you should know the limits of the pulse, right? Read the pulse, know the limits. There are many formulas to estimate the first natural periods. There are many. First primary natural periods are normally estimated by number of formulas. The most simple formula is related to number of stories. So people say number of stories divided by 10. That's not really something that you can lock it, but okay, it's a good number to start with. It depends on many things. So which means if it's, let's say it's he gave me the example of 50-story building or 60-story building. It's a 50-story building, you should get the number between 4 to 6, right? 5 being in the middle, plus minus 20%, and those variations can come from many reasons, right? But if you're getting a natural period 1 second for a 60-story building, you must be alarmed. What happened? Or if you're getting 10 seconds, you should be alarmed. What happened, right? Or even 7 seconds, you should start to worry. Even 3 seconds, you need to understand why is it happening. So then you need to investigate and find the reason. If you can find the reason, it's fine. Now that's simple, one way. Then we look at so you can check the model or the structures overall. I would say, I wouldn't say correctness or reasonableness by using the primary mode value, right? But it's not a very good indicator. It has many problems with that. We will talk about that in a minute. Second thing is, how is it deforming? So that's number one. How is that particular mode, how is the structure deforming in that mode? That will give you information about whether the structure is symmetrical or not symmetrical, whether it's eccentric or not eccentric. It will then start giving you more information about the structure, right? So the shape combined with the number starts to give you more information, and then second mode gives you more information, third mode gives you more information, fourth mode gives you still more information. So you can keep on going below and looking for higher and higher and higher modes and start getting more and more and more and more information. You can keep on going deep, right? And every mode has a meaning. We just have to find what that meaning is. There will be maybe some modes which are only, what should I say? Let's say if this, okay, continue the discussion. Let's say it's a 50-story building and you are getting some mode, I don't know, mode number what, doesn't matter. And the natural period of that mode is 1/20th of a second, right? Or 1/10th of a second. You might say, oh, what is this? But that has a meaning, because that could be the vibration of the floor where you are walking, right? That could be the floor, natural frequency of the floor. That could be in that range. And we need to worry about that, because when people are walking on the floor or they're dancing, right, on a disco floor, or disco is not in fashion anymore, okay, some other dance, then if the floor is not designed properly, that could be a problem, right? You often walk and you see the floor. In Bangkok, there's so many steel bridges, and when I drive there and I park my car, I'm not parked, the traffic is jammed, which is most of the time is jammed, so it's like a parking. And then a bridge, little bit next to that, also steel bridge, and a bus goes, and my car is doing like this, tick, tick, is jumping. I'm almost, first time I was saying, what happened? I was trying to get out of the car, what happened, right? The bridge is collapsing or something. Because it's a steel structure, it's very flexible. And then another steel structure connected to that one, where the lanes are moving, the buses move and they vibrate the structure, which is the natural frequency, so that it just pushes the car up like that. And if you're not familiar with that, you can get scared, right? So that means those dynamic response of those bridges has not been checked carefully enough. The effect of this has not been tested well. And then actually Professor Pennan got a project to check the dynamic response of 14 steel flyover bridges in Bangkok and fix it, because people got actually worried and they were saying, what is this? You know, bridge is supposed to be solid thing, not a swing, right, or a roller coaster. Anyway, so you need to look at all that, and this was because of resonance. Resonance is when the natural frequency or natural period of frequency of the structure starts to coincide with the force frequency. That means if the slab is going down and the load is also going down, every time it's like a swing. So if you're in a swing, you know how to go higher, right? You push when you are going this way, and you keep doing that in a systematic manner. You are utilizing the natural period of the rope and synchronizing with your force. That's why you can keep going higher. So this will not change the period, but it will change the displacement of the, so you can change the displacement of a structure by synchronizing your force application with the natural frequency of the structure and create displacements 10 times larger than what you could otherwise create due to resonance. Or you can do the other extreme. You can suppress the vibration of a floor by applying a force which is opposite to that and stop the floor from vibrating. Because if the natural frequency is this one, you apply the force exactly but in opposite direction, and then not let something vibrate. And that is how the dampers are designed. That's how so many motion control devices are designed, right? So it is all about dynamic response. So natural period, the heartbeat indicates stiffness and mass relationship, basis for damping, resonance, amplification effects. Many relationships for tall buildings and others exist, right, to estimate that. And then measurement, we actually can measure the natural frequencies of the structure. So this is important. Not all of the modes are significant, and that's the problem. Modal extraction, we need to be able to search which one are significant and which one you can neglect. How many modes should be studied, right? Sometimes local modes may disrupt the modal participation. Sometimes if you don't connect the model correctly, some local modes come in between the primary modes and destroy your, so you have to eliminate them, right, or lock them or block them, so that otherwise they will mess up with your results. So this is a very old slide, I still use it, I don't know why. So this is a symmetrical building, this is unsymmetrical building. So most, theoretically speaking, don't believe it too much, because exceptions exist for everything. If your building is symmetrical, you should get these 3 types of modes. That means you should get first mode to be translation in one direction, weak direction, second mode to be translation in the other weak direction, and third mode to be a torsion. So these 3, this is the response of a typical well-behaved, good boy kind of a building which should exist, and then these modes will repeat. first 3 will be like this, next 3 will be again like this, but second mode of vibration of each. So this is another important thing to understand what is first mode, second mode, third mode. When I say first mode, second mode, third mode, in one context this is 1, 2, 3, but in a tall building context this is not the way that I would like to look at it. I would like to look at it the second mode in the same direction, which is the fourth mode, and I would like to look at the second mode in this direction, which is the fifth mode, and so on. So we have to look at the modes in different ways and understand them. So numbering of the modes is not the same the way that we are looking at them for contribution to structural response, right. So that's also very important. And if the structure is unsymmetrical, the first mode can be torsion, right, because the shear wall over there shifted the stiffness center. So now the mass center and stiffness center are not aligned, so buildings start to twist, in which case the first mode will be torsional even if there is no eccentricity of the mass of the stiffness. It is possible because if it's a especially tall building, because if it's a core wall right in the center completely symmetrical, then in that case the lateral stiffness of the frame is quite large, but torsional stiffness is very small because the core is right in the center. So the columns around that are not providing enough. It's a flat slab, especially a flat slab building with a central core will typically have a torsional first mode, because the building starts to rotate about the core, because you do not have end frames stiff enough. Because remember, I told you first the structure will move in its weakest mode, that is the first mode. So because the outer frames are very weak relatively to the core, so they cannot prevent the building from twisting. So the building starts to twist before it can deform, because the deformation is being controlled by the core wall in its axial is its bending stiffness, but core wall does not have the torsional stiffness to hold the entire building. That should come from the outer frames, which are weak because it is a flat slab. So which means that completely fully symmetrical buildings with mass and center and stiffness completely centroid, no foundation problem, no nothing, can still have torsional first mode if the outer frames are weak and the core is strong. Next question that I get all the time after that is such building acceptable? Because normally for the tall building design or any building design, we do not recommend the first two modes to be torsional, because that means irregularity, that means not good. So generally in a good practice, this kind of behavior needs to be avoided. You should not have torsion as a first mode, because it creates problem with the column forces and so many things. So you do not want that. Why? Because if the building is twisting, then this column will get more force than these columns, and its likelihood that that column will fail in shear, because now that poor column is the only one trying to hold the building from rotating. So all the force will go to that column. So we do not want that. So that is why we do not want that. But on the other hand, this mode that I am talking about, the torsional mode of a perfectly symmetrical building, is not so detrimental. Why? First of all the columns are equally spaced and they are sharing this one. That is number one, that is good point. Second is, it is not involving the movement of a lot of mass. Most of the mass is not moving. So the force generated is very small. It is a torsional movement, right? That means there is no net movement of the building. So that means the mass, the force, the base shear generated is 0. It is only a small force is being generated in the column, but net base shear. So that is another characteristic of a perfectly symmetrical torsional mode, that the base shear corresponding to that mode in an earthquake will be 0 or nearly 0. So you do not need to worry too much about, only need to worry about the design of those columns for that eccentric force, which, like you said, all the columns are there, so it may not be that big. So you have to understand, you have to know the rules and also know when to break them. So this is one instance where you can break the rule of the symmetrical or the first modal, first mode being torsion, right? And even I also understood this much later. I also used to worry, what happened, this building, why is it twisting? You know, it's so symmetrical. Then we sort of looked into that and understood, oh, that's what's happening. Okay, this is very important. This is a very important slide. I expect all of you next time when you talk about tall buildings and modes, I expect you to make the diagram like this in your thesis, in your presentations, in your class projects. Never tell me about mode 1, mode 2, mode 3 in the natural order. Show us the modes like this. I would like to see, and Professor Penning also, all of us would like to see you talk about the modes in this matrix form. So what does it show? It shows you 3 modes in one direction, 3 modes in one direction, and 3 modes in torsional another direction. So first 9 modes are being represented, but not in the number that the program will give you. You need to put them in the order, in the direction. So these are called directional modes. You need to separate the modes into directions. So modes must be looked at in direction way, not in number way, right? So these are the modes: first mode, second mode, third mode in x direction. This is first mode, second mode, third mode in y direction. This is first mode, second mode, third mode in torsion. But if you look at the mode actual number, this is T4, this is T7, this is T8, and so on. So the sequence number of the mode and the directional mode is 2 different things. And what we are interested in is the directional modes. We are interested in the first 3 directional modes, first 3 y-directional modes, first 3 torsional modes. That means 9 modes to the minimum. You can go higher up to 12 modes or sometimes more. But for a typical tall building, the absolute minimum is 9 modes that we would like to look at, 3 in each direction. Now look at this diagram. It is so rich if you know how to read this diagram. First of all, it gives you immediately the directionality of the modes, right? It shows you where is torsion. In this case it is third every time, third, 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 like that, right? Or second. So it doesn't matter whether it's in order or not. This is 1, 2, 3, 4, 5, 6. It doesn't matter what is the order. So we can see whether there is unsymmetry in the first set, or unsymmetry in the second set, or unsymmetry in the third set, because modes may be symmetrical in the first group, may be unsymmetrical in the second group, or unsymmetrical in the third group. So this tells you that, first of all, by looking at the number, looking at the order. It then tells you very interesting information. Okay, natural period 5.3 seconds, number 1. Number 2, 4.96 seconds. These are close. 4, 5.3, 4.9, quite close, and then 4.3. They are of the same order. They are close to each other, right? Which is a good thing or a bad thing? Actually, this is a good thing. That means the base shear and the forces generated in 3 directions will be similar, in 3 modes will be similar. So you are not expecting very large, in fact this is a good thing, because if the modes are close to each other, it's a good thing, because that means structure is behaving similarly in 2 directional, and you are not expecting that the 2 directional will interact in an unpredictable manner. So the 2 directional base shear will be similar, 2 directional displacement will be similar. So it's a good thing. That means you are going to get a good response in both directions. So having these modes close to each other is a good thing, not a bad thing, right? Like I said, you can spend hours studying this table because it has so much information. Second thing is study this way. First mode is 5.3 second, second mode is 1.28 second, third mode is 0.7 second. So you can see that there is always sudden drop in natural period when you go from one mode to the other on x direction, on the x axis. When you go in y direction, they will be similar. That means for each direction the modes jump in terms of the order of the number. So which means these modes will be higher, will be difficult to excite. These modes will be easy to excite, right? And these modes will be even more difficult to excite. So as the natural period becomes smaller, that means that mode is more stiffer. That means more difficult to excite. But at the same time, it is going to generate more force, because large stiffness means for displacement more force, right? So that's another problem. Now look at the mass participation in each direction. 60%, 66%, torsion, no mass participation. What does it mean, mass participation? That means how much percent of the building mass is moving in that mode, because that moving mass is the one which is going to be F is equal to ma, going to generate the force. So the force in the building will come from the moving mass. So that means the first mode will move 60% of the mass and generate a lot of force, right? Second mode will in second direction, 66% of the mass will moving in that direction in that mode. That means it will also generate significant force, right? Torsion does not include net force at the base, because torsion is just rotating. So there is no net force, zero. So torsional modes do not produce net mass movement. In second mode, 18% of the mass is moving, 15% of the mass is moving here, 6.5% mass is moving, 5.2% of mass is moving. So what is happening is that as we go along, as the natural period starts to be shorter, lesser part of the building moves there. And you can understand why. In this case, mass is not moving too much, because buildings moving a little bit here and there, but here all the mass is deforming. Here most of the mass is just remaining still, right? So here also most of the mass is not moving, small portion is moving. Over there the whole building is deflecting. So as we go higher and higher, smaller and smaller portions of the building are moving, oscillating in that mode. That means the mass participation is smaller and smaller, right? And natural period is shorter and shorter, frequencies is higher and higher, right? So this one picture gives you tons of information. It tells you whether the structure is symmetrical or non-symmetrical, which mode is weak, which mode is strong, which mode, what is the order of the modes, what is the modal participation ratio, and so on and so forth, right? So this picture, when I look at it, it's like looking at the pulse and understanding the whole structure right away, right? And oh no, this is not good. If I don't like it, I will tell them, oh no, this doesn't look good. Change this, because I want this like this one. This is a good well-designed building already. So this is a good. We get very funny results sometimes, right? So please remember this diagram in future. Always talk about the modes in this way. This is a very, okay, watch this one with music. Second mode in torsion mode, first torsion mode. Enjoy the music and the dance. It's on YouTube, watched a lot. So third mode, second mode, first mode. Who says structural engineering is not fun? So first, second, third mode in the other direction. Torsional mode first, second torsional mode, third torsional mode. First, second. So it has all the combinations that I showed you. We put them together so you can see how each mode compares with each other, right? So it's a minute long, I think is enough. Okay. Okay, so that tells us that there's a lot going on in a building. I just showed you first 9 modes, not even went to much higher modes, right? So each of that has a lot of significance. The higher modes are very important for tall buildings. The building codes that I keep not criticizing, keep saying that they are not applicable to tall building. One of the primary reason is that building codes methodologies are developed based on the first mode only, and they expect that most buildings response is governed by primarily the first mode, while the tall building response is affected by the higher modes as well. So this is a plot of the moment, different demands. So that we are plotting 3 demands. One is called true demand, design demand, elastic demand. Okay, don't worry about what those demands mean, but just look at so in our office in also in AIT, we use something called modal separation. Not many engineers use that in design office, not a very well known procedure, but that is to separate the response. You remember the dynamic response I showed you in the beginning, and I showed you it is a sum of all the modes. If we take the response of each mode out of the dynamic response, then it's called modal separation. And once you separate the modes and look at each mode individually, you learn much more than you can learn from the total dynamic response. So if you separate the modes and you look at the second mode, so this is the bending moment in the tall building coming from first mode. It is like bending, just a cantilever. It's quite natural, and this is what 99%, or no, sorry, little bit less, maybe 90% or 80% people believe the building's moment is coming from here. This is the moment diagram of the second mode, and here the highest moment is here, not here. Here the moment is, the difference is, no, I should have corrected that, I did not. This is 2 raised to power 9, right? This moment is 2 raised to power 10 raised to power 8. That means even though this moment is like this, actually it is 10 times smaller than that moment, which means that higher mode moment is much smaller, maybe 10 times smaller than the first mode moment, which means that the moment in a tall building is primarily coming from first mode. So that is okay, we don't have a problem with that. So the building moment can be estimated by looking at the modal first mode response in each direction. Shear is a totally different story. This is the response coming from first mode, this is the response coming from second mode, third, but look at the number here. It is the same order, raised to power 7, raised to power 7, similar number. Now we are in trouble because the shear coming from higher mode is of the same order as the shear coming from first mode, and which looks very different from a pure cantilever shear diagram. That means the shear in upper floors can be very large here, even though you would expect that the shear force should drop, we should become 0 at the top and maximum at the bottom, but there is no such guarantee in a tall building. The shear force in the middle could be larger than the one at the base, and some shear at the top may be very high that you did not expect. This completely changes the way we look at the design of the individual components, because that shear will change the bending moments in the members locally, right? And that will change the capacities, it will change the distribution of reinforcement. You cannot now say, oh, let me reduce the column size as I go up or reduce the reinforcement as I go up. It will not make sense in this context, and even higher modes are still quite large. Even this one is still of the same order. So this realization of the higher mode effects on the tall building shear contribution is very important, right? And this is something that makes the tall building design different from a typical short building design, because in short building design we do not consider higher modes, we don't need to, but here we need to. When I say higher modes, that means the each direction mode 1, 2 and 3, right? So this alone is something that we need to be aware of and need to take into account, and this is something that in research, in AIT thesis, we almost always talk about this kind of thing and work on this. This is the response spectrum of the site where the building is located. You know what's a response spectrum? Everybody knows? Okay. So two different response spectrum. This is Bangkok, this is Philippines, right? Look at the different values and shape of the response spectrum. This is mass participation, 50%, 30%, 10% for this building. First mode, second mode, third mode, right? 50% mass participation, that means 50% of the mass is moving, but the corresponding response spectrum value is very small. So even though very large mass is moving in that mode, it will be multiplied by very small acceleration. So the force generated will be very small. Second mode, 30% mass participation, but the ordinate of the response spectrum is larger, acceleration is larger, large force will be generated, and only 10% here, but the ordinate has become much larger. So even though only 10% of the mass is moving, but because of the response spectrum, large force will be generated for that mass. So that's why mass participation ratio is very critical. That is the one multiplied by the response spectrum that generates the force. So this is another case, a smaller building, 80%, 15%, 4% for a shorter building, 25-story building. So most of the mass is on a big ordinate, very small, but so the effect of the higher modes becomes less and less important as the building becomes shorter.